Hey friends, let's do number 9 on that most recent solutions homework. It gives me a balance formula equation, and it gives me a volume and a molarity. Molarity is a concentration of one of my reactants, and it gives me a volume and a molarity of the other reactant. And it tells me I observe a precipitate form, and asks me to write the overall ionic equation. I already know that even though it is not labeled AQ in this reaction, I know that my copper chloride and my ammonium phosphate are going to dissolve. How do I know that? Well, it tells me that they have a molarity. If it has a molarity, that means it's dissolved. It can't have a molarity unless it's dissolved. So I know when I split apart the ions of my copper chloride and my ammonium phosphate, they will split apart in water. So I'll be representing these as its constituent ions. However, both of my products are not going to stay dissolved. One of them is going to come out of solution. It's going to be insoluble. How do I know that? Well, it tells me that I observe a precipitate form. So when my reactants react, they're going to form one of these two things that's not going to stay dissolved. It's going to come out of solution. I've got copper phosphate and I've got ammonium chloride. How do I know which one is going to stay together? It's not going to dissolve. Well, look at my solubility table. Let's check them out. One of them was copper phosphate. I already see right here, most phosphates are insoluble, and copper is not one of the exceptions. So I'm already thinking, well, dang, already looking at copper phosphate. Probably going to be my insoluble one, probably going to be my precipitate. Well, what's my other product? Ammonium chloride, NH4Cl, and ammonium, NH4, is a polyatomic ion. You just need to kind of remember that that's its name. You can also look on reference sources like the back of my periodic table. Oh, look, it says NH4 plus is an ammonium ion. Awesome. All right, so let's look at this, ammonium chloride. I already see most chlorides are soluble with some exceptions, and ammonium is not one of those exceptions. All right, already looking like this one's going to be the one that dissolves. If you remember that NH4 was called ammonium, you would also see that most ammonium compounds are soluble. So that's 2 points in favor of ammonium chloride being soluble, staying dissolved, and also looks like copper phosphate is going to be the one that stays stuck together. It does not dissolve. It is going to fall out of solution. It's going to be solid. So that means this reactant, and this product, I'm going to have to bust apart into their ions. Let's do it. All right. Here's the steps. I'm going to take these apart one by one. All right, copper chloride. Let's split them apart. We know they dissolve, so they're splitting apart into their constituent ions. I'll Cu, and I'm going to put a little AQ here because I know it's going to dissolve. And Cl with a little AQ because it's going to dissolve. Might be thinking, where's your little 2 subscript? You don't put it there. These 2 chlorines, when they dissolve, are not stuck together anymore, which this 2 represents. They are off on their own, living their best independent lives from each other. So how do we represent that? Well, we take our coefficient. If your molecule has a coefficient, it always has one. It might just be 1 and be invisible. And you'll go ahead and apply it to each one of your constituent atoms here. So I've got 3 coppers right here. I just go ahead and put my 3. Beautiful. And I have 3 Cl2s. But when this dissolves, since this 1 copper goes off one way and the 2 Cls go off independently in separate directions, I need to multiply because every one of these CuCl2s that break apart is going to produce 2 chlorines. So I have to multiply. Take my coefficient, multiply it by the subscript, and I'll get the new coefficient for chlorine. So 3 times 2, going to be 6. All right, so I've got my numbers here. Now I need to get the charges. The first ion in your compound is always going to have a positive charge. The second one is always going to have a negative charge. That's just how we write them, by convention. How do you know what the charges are? Usually, not always, but usually, you can just look at the subscript of one of the atom's neighbor to see what its charge will be as an ion. So let's look at my copper. I was looking for my charge of copper. I know it's positive, but how positive? Is it +1, +2, +3? Well, let's look at the subscript of its neighbor. The subscript of its neighbor is 2. So we just bring that up here and write that it has a charge of 2+. What about chlorine? I know it's negative, but how big is that charge? Well, let's look at the subscript of its neighbor. That Cu has an invisible subscript of 1. So we just carry it up here. And you could write the 1 right here, that's fine. But by convention, if it's 1, we just don't write it. So if you just see a minus or a plus by itself, it means 1. Beautiful. Let's say we wanted to confirm that. How do I know? Maybe this was an exception. How do I know that chlorine really has a -1 charge? Well, just pull out your periodic table. And you might see, oh yeah, chlorine is one of these group 17 elements right here. It wants to gain 1 electron to finish its valence shell and be nice and stable. So since it's gaining 1 electron, that's going to be a -1 charge. So it tends to have a -1 charge, and that is what we found right here. All right, let's break apart our next one. This one is a little more complicated. This one is made of 2 polyatomic ions. NH4 is a polyatomic ion. It is ammonium. We talked about that one already. And PO4 is a phosphate ion. We mentioned the name of it, but we didn't talk about the fact that it's a polyatomic ion. What does that mean? That means you're treating those polyatomic ions, NH4 and PO4, like they are one unit. They do not break apart. This N and H4, they stay stuck together when they dissolve. They don't come apart. This P and this O4, they stay stuck together. They don't come apart. However, the whole NH4 unit and the whole PO4 unit will separate from each other. These are just 2, think of them as giant ions. They come apart from each other, but within themselves, they stay together. Why? It's because they're covalently bonded together. This nitrogen and these 4 hydrogens are covalently bonded. They share electrons. That's a very tight bond. This phosphorus and this 4 oxygens, they're covalently bonded together. It's a very tight bond. They don't come apart just because they get wet and get in the water. However, the NH4 and the PO4 as the separate units, they are just attracted to each other because of their opposite charges. If I look at my list of polyatomic ions, I see NH4 has a positive charge and PO4 has a negative charge. So they have opposite charges, so they're attracted together. However, that's not enough to keep them together when they get in water, and they'll get pulled apart. So we're treating this as a unit, and this is a unit. Let's start with the NH4. Just copying it down. AQ, because it's dissolved. Don't forget your AQ. Be ashamed to lose a point because you forgot your AQ. It is part of the overall ionic equation. And your PO4. AQ. There we go. All right, how many of each one of these do we have? All right, I see that my whole unit, NH4, has a subscript of 3. So in each one of these molecules, there's 3 NH4s. And overall in my balanced equation, I have a 2 for a coefficient. So to get the number of NH4s in solution, I do 2 times 3. Boom, 6. PO4. Remember, it's an overall unit. A lot of people might mess up and think, oh, it's got a subscript of 4. No, that's the subscript of the oxygen. That's not the subscript of the PO4 altogether. You need to kind of imagine that there are parentheses around this. And this is the real subscript for your phosphate polyatomic ion right there. So really, its subscript is 1. So I'm taking 2 times 1 and getting a 2 for the coefficient for my phosphate right here. All right, how about the charges? I know ammonium is first, so it has a positive charge. Phosphate is second, has a negative charge. In this case, using the subscript of its neighbors will work. Let's look for the magnitude of my charge of my NH4. Subscript of its neighbor is a 1. Let's copy it up here. Oh, it's a +1, but I'm not going to write the 1 because by convention, if it's 1, you just don't write it. Let's look at my phosphate. Subscript of its neighbor is 3. So I'll carry it up here. So the charge of my phosphate ion is a -3. How do you confirm that? Well, either you just have memorized the charges of your polyatomic ions, or you use your cheat sheet. I like to use the cheat sheet. Sure enough, NH4, this tells me it has a charge of +1, which is exactly what we got. My PO4, there we go. It has a charge of -3, which is exactly what we got. Amazing. All right, let's move on. Making sure I've got coefficients, I got charge magnitudes. They're all tagged with AQ because I know they all dissolve because they all were given with a molarity. All right, I'm out of room, so I'm going down a little bit. All right, Cu3, PO4, 2. All right, how is that one going to split apart? It's not going to split apart because we already figured out that it's insoluble. Water can't pull these coppers away from these phosphates. So we just write that sucker down as is. This is the easiest one. You just copy it. I'm copying Cu3. I'm copying PO4, 2. And we just mark it with a little S for solid. Doesn't dissolve. It's our precipitate. All right, moving on. We identified that's the one that came out of solution, so the other one must stay dissolved. Here it is. Let's pop it apart. Remember, NH4 is a polyatomic ion. N and H4 are covalently bonded together. They're not going to come apart, but they are going to separate from the chlorine buddy. And let's write down that chlorine. Don't forget your AQs. All right, how many do we have? Remember, this NH4 is a unit that has invisible parentheses around it right there. It has a subscript of 1, and we got 6 of them. 6 times 1, 6. Chlorine has an invisible subscript of 1. 6 times 1, 6. Just lovely. How about the magnitude of those charges? Which charge is it first? We got to figure out which charge. NH4 was first, so it's going to be positive. Cl is second, it's going to be minus. Let's look at the subscript of the neighbor to see the magnitude of that charge. Neighbor of NH4 is Cl. Its subscript is 1. So that means I probably got a charge of 1. I'm not going to write the 1 because I don't have to because it's 1. Any other number, you got to write. But 1's easy. Just leave it. Plus. Chlorine. Now, the subscript of his neighbor is not 4. No, don't do that. Don't make that mistake. 4 is the subscript of your H. It's not the subscript of your overall NH4 polyatomic ion. Its subscript is 1. So you just take that 1, put it up here. Well, but you can be lazy and skip it because it's 1. You can just leave the minus. So there we got it. This is the answer to 9A. That is your overall ionic equation. Isn't it lovely? What does 9B ask for? Write the net ionic equation. All right, net ionic equation. Let me grab another pen. We need some more color in here. Oh no, my cushion fell. That was elevating me to a proper height. Okay. A net ionic equation is only showing the individual things in this reaction that actually change. What does that mean? Well, let's look at the reactants and the products in our overall ionic equation. We got 3 coppers over here in the reactants, but here's our 3 coppers in the products. This copper has changed. It's gone from being an ion floating around in solution to being stuck onto this phosphate. It's changed. So we don't touch it. We just leave it how it is. But look at this chlorine. We got 6 of them as ions in the reactants, and we got 6 of them as ions still floating around in the products. They didn't change. They just sat there and watched. That means they are spectator ions. If it's a spectator ion, you can put a little cross through it like this. Look at our 6 NH4s. They're unchanged by the time we get to the products. They're exactly the same. That means we can just kind of cross them out. What about our 2 phosphates? They have changed. In our reactants, they're just floating around in solution. They're dissolved, but in our products, they are now stuck onto these coppers. They've changed, so we don't cross those out. Now to get our net ionic equation, we just recopy this whole thing, but we do not include the ones that we crossed out because they were identical in the reactants and the products. So I'm just going to recopy 3Cu, 2 plus. Don't forget your AQ. I'm skipping this one because I crossed it out because it was identical in the products. I'm skipping this one because it was identical in the products. I got to write this one though because it changed. 2PO4 AQ 3 minus. And I'll recopy my precipitate product because it changed from the products to the reactants. Make sure I get that S on there. And you're done. That's it. That's your net ionic equation. I might also ask you to identify the spectator ions. Your spectator ions are just the ones that did not change. So my chlorines and NH4s are your spectator ions. You don't have to write 6Cl or anything like that. You can just write Cl minus and NH4 plus. That's your spectator ions. Just like if you were in the stands at a football game, yeah, you're there at the game, but you are a spectator at that game. You're there, but you're a spectator. Just like these things. They're there, but they're not actually playing the game. They're just still floating around watching. All right, lovely. Let's look at the next part. 9, there we go. 9C, identify the limiting reactant. First thing we got to do to identify the limiting reactant is we got to figure out how many moles of each one of those two reactants that we've got. I'm going to put this thing right under here for easy reference. All right, so it tells us that we've got 70 milliliters of 0.5 molar CuCl2. So I can use that to calculate the moles of that first reactant, CuCl2, and I've also got a volume and molarity of my second reactant. I can use that to calculate the moles of my second reactant. Once I got the moles of both of my reactants, I can figure out which one is limiting. How do we figure out the moles? You use this one. Molarity equals your moles of solute over the volume of your solution. Volume has got to be in liters. All right, let's do this for our CuCl2. We are given that the molarity of our CuCl2 is 0.5. We're trying to solve for the moles of it. And the volume is 70 milliliters. You've got to write it in liters though. So it's the same thing as 0.70 liters. Now do your algebra, multiply each side by 0.07 to solve for moles of solute. And I believe that will get us 0.035 moles. All right, that's how many moles, sorry, I was off screen. That's how many moles of CuCl2 we've got. What about our other reactant, our NH4, 3, PO4? Well, it tells us that the molarity of that solution is also 0.5. And the volume of it is 30 milliliters. I got to make sure I convert that into liters though. So I'm going to write it as 0.03. You just divide by 1,000. And in this case, I will get that I have got 0.015 moles of ammonium phosphate. All right, beautiful. I got my moles of each. Now let's use that to figure out the limiting reactant. How do you find the limiting reactant? I'm going to remind you. What you're doing is comparing one of your reactants to your others. I'm going to recopy the reactants portion of our balanced formula equation just for reference. Here it is, so that way I don't have to keep flipping back and forth, or you don't have to keep trying to rewind or look at your notes, because I know you didn't take any notes. All right, and just as a reminder, I'm going to write the moles of each one underneath. So we calculated that we had 0.035 moles of this one, and we calculated that we had 0.015 moles of this one. So you just set up a ratio to compare one to the other. You can start with your NH4,3PO4, or you can start with your CuCl2. Doesn't matter, it'll work either way. I'm just going to start with this one. And maybe I'll do it both ways. All right, so you just write down the actual number of moles that you have of one of your reactants. And then you multiply it by a ratio of the coefficients. Ratio of the coefficients from your balanced equation. On the bottom, you put the one that is in this position right here, CuCl2. It goes on the bottom. On the top, in the numerator, you put the one you're comparing it to, NH4, 3, PO4. And you're just getting your coefficients from your balanced chemical equation. And again, this is just right off of this equation right here. Just rewrote it big right here so you can see it better. So CuCl2, the coefficient is 3. NH4, 3, PO4, the coefficient is 2. Solve that, and let's see, can I get this? Oh dear. I did not do this math ahead of time, so I'm going to have to do it cold right here. So I'm taking 0.035, 0.035 times 2, 10, 6, 7, 0. All right, 0.70. Easy. And now I got to divide it by 3. Oh, my Lord. Let's see. 0, 2. I haven't done long division since who knows when. Well, let's call it that. All right, so this is what I get. Equals 0.023 moles of NH4, 3, PO4. CuCl2 cancels, so I'll be multiplying my 0.35, the actual moles that I have on hand of my copper chloride, and multiply it by this coefficient, divide it by this coefficient, and you get this. All right, how do you interpret this result? It's like this. This is how you word it. Say that, okay, if I wanted to use up all of my copper chloride, all of my 0.035 moles of copper chloride, I would need to have 0.023 moles of ammonium phosphate. So if I wanted to perfectly react in a reaction, use this all up, I would need this much ammonium phosphate. Well, let's compare it to how much ammonium phosphate we actually have. Oh, we've only got 0.015 moles of ammonium phosphate. We would need 0.023 to use up all of our copper chloride. So if we need this larger amount of ammonium phosphate and we have a smaller amount of that instead, that means that before we use up all of our copper chloride, the ammonium phosphate is going to run out. Because to use up all of this, to react all of it, we would need this larger amount. We don't have it, it's going to run out first. So that means that NH4, 3, PO4 is our limiting reactant. Perfect. All right, let's see what's next. That was the answer to C. Now we got D. How many grams of precipitate should you expect to form? All right, here's how you do that. If you need to figure out how much of a product you form, then you take your limiting reactant. So our limiting reactant, we concluded, was NH4, 3, PO4. We take the actual amount that we have on hand. We have 0.015. And we use our limiting reactant because the reaction will stop when we have run out of your limiting reactant. When your limiting reactant is used up, that's when the reaction stops. And so that determines how much of your products you form. So again, we're multiplying it by a ratio. And in this case, what we're looking for is the amount of product that we're going to form. So we put our product on the top, which is our precipitate, Cu3PO42. And on the bottom, you always put the one in this position, NH4, 3, PO4. And you just take the coefficients from the balanced chemical equation. Let's look at it right here. Again, coefficient for my NH4, 3, PO4 is 2. I'll just copy that in. Coefficient for my copper phosphate is 1. So I'm just going to write that in. This will cancel. And it will turn out that I believe I've got, oh dear, I'm gonna have to do it again, aren't I? All right, so this is just 0.015 times 1 and then divided by 2. Let's watch me struggle through some long division I probably haven't done since 5th grade. 0.0, oh boy, 0, 7, 14, 1, 0, 0.0075, there we go. If I was well prepared, I would have done this math beforehand. All right, so I will end up with 0.0075 moles of copper phosphate. And again, I take my limiting reactant and just multiply it by the ratio of the product that I'm looking for over that limiting reactant. All right, the question, though, is asking for the grams of precipitate. This is giving me moles of precipitate. But at this point, it should be pretty straightforward to convert moles into grams. You use this formula. There are other ways to do it. This is how I like to do it. Moles equals mass in grams divided by formula mass. I know my moles. It is 0.0075. I'm looking for that mass in grams. Luckily, I already did this beforehand. The formula mass of copper phosphate, adding up the atomic weights of 3 coppers, 2 phosphates, and 8 oxygens, should give you 380.58, which will give you a mass of 2.854 grams. Just multiplying both sides by 380.58, and that'll give me 2.84 grams of my precipitate. All right, you still with me? We're 25 minutes in. That was the answer to number 9. That's the grams of precipitate will form. Last part, though. How many molecules of precipitate should you expect to form? Well, we can convert our moles into molecules of precipitate too. Just as a reminder, the number of moles of precipitate we calculated we had, which I awkwardly did on the spur of the moment with long division that I haven't done since 5th grade, was 0.0075 moles of Cu3 PO4 2. You can convert moles into number of molecules also. Remember the avocado number? Moles. Number of molecules divided by 6.02 times 10 to the 23rd. Let's just plug in our moles. 0.0075 equals number of molecules over avocado, 6.02 times 10 to the 23rd. All right. Now, to solve for number of molecules, you multiply each side by 6.02 times 10 to the 23rd. So I'm multiplying 6.02 times 10 to the 23rd times 0.0075. Luckily, I did this already. And you'll get 0.0452 times 10 to the 23rd. That's a fine answer. However, by convention, in scientific notation, you put the decimal after the ones place. So let's convert this to extra proper scientific notation. So I'm going to move that decimal 2 places. Ring, ring. That sounded like Hubert jumping in that old arcade game. 4.52 times 10. Well, we got to adjust this number too, since we adjusted this one. I made this one 2 decimal places bigger, so I need to compensate by making this one 2 decimal places smaller. So there we go. We will have produced in our test tube 4.52 times 10 to the 21st molecules of copper phosphate. I'd accept this answer too, but for future reference, get in the habit of putting it like this. And then we're done. We did them all. We did number 9. We did all kinds of stuff. We did overall ionic. We found some moles. We did a limiting reactant. We found amounts of precipitate. Awesome job. Watch this video. Let me know if you have any questions. I'm here for you.